Welcome to the channel where all you gotta do is design a shock dyno. I know I got too much stuff in my shop already, but I have a bunch of work to do on the shocks for the Mustang and the shocks for the race car and the shocks for the Bronco, and it seems like every time you walk into one of those places they want $1,000. And so I told myself, if I can build one for $1,000, because my time's worth nothing, basically, I'll just build one, and then I'll have it to use whenever I want for my, the Birkin. I need to revalve the rear shocks on the Birkin because those nitrons were made for a Lotus Elise, and I have it on something with way less. Anyway, for another story. But anyway, I'm designing a shock dyno. So if you don't know what a shock dyno does, it's some sort of an actuator. Could be pneumatic, could be hydraulic, could be crank, could be a Scotch yoke, could be electro, like a linear motor, but basically something that moves the shock up and down. It compresses it and then it rebounds and compress and rebound, compress and rebound. And you basically have to know where it is, and you have to know time, so you can calculate the velocity. You just take the derivative of position versus time, and that gives you the first derivative, which is velocity. And then you want to plot the velocity versus the force. So the first thing I did was, since I don't have any fancy software, I don't have Python or MATLAB or anything like that, I have Excel. So I just made some fake data up, and I said, okay, well, this is what the velocity is going to be. It's going to kind of look like a sinusoidal wave-ish. So I kind of made a sort of sine wave. It's actually piston motion because I have a program for piston motion, so I put some generic numbers in there for piston motion. I got kind of a sine wave. It's sort of not, but it's close. And then I kind of just drew a force equivalent wave, that what it's going to do, and it's going to cross through zero when it's turning directions, and it's going to be zero then. And then I made a spreadsheet, and it wasn't 20 minutes or something, and that spreadsheet to kind of show how that works. I cartoon something up in SolidWorks. So this is my shock dyno design, and basically what you need to understand about how shock dynos work is there's a load cell up at the top here, and this is the load cell, and you can't push on the load cell sideways. You got to kind of push on it straight. So you can't have something that has a load cell like this and then it has a force going like that and like that, and that will, not only will it throw the data off, but will ruin the calibration of the load cell. So you basically have to have, either you have to have the load cell between two things that can only go straight up and down, or you have to have your shock absorber in between something that can only go straight up and down, or both. So in this particular case, I made it so the shock absorber goes straight up and down and goes through the load cell perpendicularly. And the way they did that is, let me hide some stuff here. These are just kind of brackets here. Move those out of the way, and you can see I got this. It's basically a gearbox, a worm drive gearbox, and then I got it mounted to this, basically a crankshaft. This little blue thing's a crankshaft, and when you crank that around, it goes up and down. And of course, variable speed motor. You can run that at whatever speed you want. And this particular one has two different strokes, so you can change the stroke of the crank, and you can also change the stroke of the piston by changing where the connecting rod goes into this A-arm kind of setup. Unfortunately, this got kind of complicated because this thing's got to go straight up and down, and then this A-arm is going to articulate, so the hypotenuse can get shorter, blah, blah, blah. So it has to have these roller bearings here and these pusher puller things. And then this is essentially just a linear guide on this side, and another linear guide down here, which is just a hole in a piece of aluminum right now, so that really wouldn't last very long. And I added up how much it was going to cost just to buy the material for this, and it was close to the $1,000 just in the aluminum cost. Not close, I think it was like 600 or something like that. But you got to buy a motor and a motor controller and, you know, load cell and instrumentation for the load cell and yada yada yada. So that wasn't going to work. The other thing I didn't like about this design is you have to mount it to a table that has basically a hole in it. You can't just like mount this to the floor or whatever. So that's kind of not ideal. I did make some adjustment here, so if you want a different length shock, you can just take this thing out. You got to pull the bolt out of here and out of here, and then move it up to the next one. But the next one's like 3/4 of an inch away, so as long as you have a shock with quite a bit of travel and you don't need to, you know, get it precisely located, then this would probably work. But the switch over time would be long, right, from this length shock to another length shock. And then if you wanted to make it like for a really long, like the Bronco has 14-inch travel shocks, so this would have to get even taller than it is right now. So anyway, this is typical high design stuff, right? I make some napkin sketches in my notebook, and then I put it to CAD, and then I go, okay, I see what the problems are, and then I throw it all away and I start over. So this is starting over is version 2. So this is Shock Dyno version 2. So I changed a few things. I made these bars a little bit thinner. Half as much aluminum means half as much money. I also mounted the gear motor on the bottom, but as you can see, it still sticks out a little bit. The motor will stick out a little bit, but you know, you can put some little feet under there or whatever, and it'd be fine. Kind of has the same setup for the crankshaft, right? This thing goes round and round, and it's 2 different crankshaft strokes, and then the A-arm has 3 holes in it. So that kind of was carryover, but what I did get rid of is the big rod sticking through the bottom, and now this just has the shock absorber is on the A-arm. So now the shock absorber is going to push on an angle as that arm, you know, the A-arm pivots. It's going to move it, not a huge amount. The A-arm's, I don't know, 10 inches long or something. I forget. Let's measure it. We got the technology, and I drew this months ago, so it's 10.34 inches. So yeah, so it's fairly long, but when you get to a high travel, it's going to put quite a bit of a side load on it. So on this particular one, what I did is this here is a linear guide. Essentially, there's little ball bearings in that guy, and so that takes all the side load and transmits it into this load cell straight. But this was still kind of expensive for one, and two, I'm not sure that you really want the load cells to be able to flex, because that's how it's measuring. It's basically a strain gauge inside of an S. So as it strains, it shows you that response. And this one, it can't really strain because it's constrained on this end and it's constrained on this end. So I think that's going to throw my load cell. I'm not an expert on load cells or shock dynos for that matter. So anyway, I kind of abandoned this one, and this was still, you know, a lot of aluminum and a lot of expensive stuff. So I still wasn't going to get under my $1,000 goal. So this is my version 3, and as you can see, it's similar but different. So I still have my same motor. This one actually drew the motor because it showed up in the mail, so I can measure it. And this is the same gearbox. This is like a 1.75 horsepower rating gearbox. Supposedly it's 75% efficient, but I find that kind of hard to believe. And this is a 3 horsepower motor, 3-phase, so it's variable speed. As you can see, I significantly simplified the A-arm. So the A-arm is basically just a piece of steel with some holes drilled in it and rounded edges. So this piece and this piece are separate pieces, so I don't have to worry about getting that perfectly perpendicular. And then this just says a through bolt and a heim joint on this rod here. And the purpose of this rod is this is how I take up the adjustment. You know, left-handed heim on this end and right-hand heim. And just this end you can make small adjustments, and then for big adjustments you could just get a piece of hex bar, and you could have a 2-inch one and a 3-inch one and a 5-inch one and a 12-inch one, whatever. And then that would allow you to run long shocks and short shocks. And then I found these linear guides. This is like 25 millimeter guide rod. So this has like a linear ball bearing guide. This piece, this piece, this piece, this piece. So I just kind of added those together. So I have a little bit more L over D. And then all the side load is going into these two pairs of linear guides. So that should give a nice straight actuation to the load cell. And then of course I have a heim joint on this, and the load cell can articulate all at once. So that's good. I also made it out of steel. Typically you want this structure to be as stiff as possible. And the reason for that is the way most people make these, and actually the way they make like a pull tester, like if you want to take a sample and see how strong it is and pull it, you want to make that system really stiff. But that's not what people do. People make them thin, and then they look at the load and they go, well, the stretch of the equipment is this much because we already calibrated it, and you just take that out. I don't like doing stuff like that. So anyway, I made this less stiff, knowingly not less stiff. This is steel, but still less stiff. But instead of just knowing what the position of the actuator is, whether it's a linear actuator or a crank, or what most people use in the industry is a Scotch yoke, so you get pure sinusoidal motion on it. Instead of doing that, what I've done is I just put a linear transducer on here. And the linear transducer is to the eyes of the shock. Not really, but this bolt would be rigidly attached to the swivel on each end of the shock absorber, whatever shock absorber you happen to have. And so it's measuring the actual length. So if this thing stretches, it doesn't matter. It changes your stroke a little bit, but it doesn't change your velocity, right? Really what you care about is how far that shock absorber is moving relative to time. Take the first derivative of that and you get velocity. So I put my transducer on here. Now that's going to make it a little bit more time consuming to put a new shock on. You got to make sure, you know, but I'm in the production shop. I want this thing to work. And if it takes me 5 minutes to set it up instead of 5 seconds, it doesn't matter. And I really think it's only going to be another 20 seconds or something. So anyway, this is the final design I came up with. Nothing's really final because you know I'm going to change it. If you watched any of my videos, you know I'm going to change it. But I already all this material I already have in the wine cellar, but it's probably like $100 worth of material. So that's fairly inexpensive. Linear transducer was another $100. So that's fairly inexpensive. But I only have 1,000 to work with, right? Also, I bought this motor from Surplus Center. I forget how much it was, $150 or something. I'll put it up in the corner. And then the most expensive part, obviously, was this gearbox. That was $276 or something like that. And then all the rest of the stuff is just like little pieces here and there. Some stuff I'll have to, you know, have to go to the metal store and get this piece and get these pieces and whatnot, and some welding rod and some argon. But the linear guide thing was like 70 bucks or something shipped. And the strain gauge, I found a brand new strain gauge on eBay for 20 bucks. It was somebody bought it and then they didn't use it, so. And I think this one's like 300 kilograms, so that's about 660 pounds, 670 pounds, something like that. So should be fine for what I'm doing. So anyway, yeah. Then I got my, you know, data acquisition box, which I'll show you in a little bit. And that, of course, had a little bit of, you know, I didn't understand 100% what I was doing. I'll explain that when I go over the electronics part of it. And then I also ordered a variable speed drive for this 3 horsepower motor. I think it's 3 horsepower, it might be 2 horsepower. Anyway, this motor. And that was like 75 bucks. So if you add all this stuff up, I'm, you know, getting close to like $800 or something. Which is close to $1,000. If I go, you know, if I go a little over, that's fine. Okay, so here's the spreadsheet that I came up with, and this is basically your travel data, but you don't know the length of the shock, so I just calculated the max and the min, right? And then I subtracted those two and did a little bit of magic-y stuff here, and then so now I have like an actual, you know, this is how much travel it has, goes through 0, right? So it automatically figures out 0 travel to 100% travel. And then this is the timestamp, this is the travel, this is the timestamp. And then if I do some basically derivative delta, it's basically dx dt or dy dt, whatever you want to use for a variable for the y is typically used. That's why KYB shocks are named KYB, so we'll call it y. So the delta between the time versus delta between the displacement, and that gives you velocity. Right here, that's velocity. And then I don't have real data, so I just basically I multiplied the velocity times 30, and this would give me like a force. In real life, I'll have a real force data. And then I have another one where it just takes the absolute value of that. And then I plotted it. And I mean, normally this would kind of be like that, depending on if it's, you know, linear or regressive or whatever. But this is basically, you know, what you look at on your Shock Dyno curve. So I won't be using any of this. Well, I'll be using some of this. I'll be using the first, I'll be using the data, and I'll be using the timestamp, and then over here for the force, I'll have actual force that corresponds with this timestamp. So I'll be using everything except for this whole thing is made up. It's just a multiply the velocity by 20, and then I'll have a plot. And then for each velocity, right, because I'm gonna have a variable speed motor on this, I can change the speed. And then there's different clicks. All my shocks have like adjustments on them. So there's an adjustment for bump and another adjustment for rebound. So you can run a variable speed and get one curve at this speed, one curve at that speed, so you can see what the clicks do. And so I'll have to do a little bit more refinement on the. This is like start Shock Dyno. Yeah, there will be many more things happening on this. And yeah, I don't know what this force is going to go up to, but I can make it auto scale, I can change the scale, whatever. So the nice thing about Excel, a smart guy once told me that Excel is the second best program for everything. Like if you want to write a novel, It's not the best program, but it'll do it. If you want to, do math or accounting, it'll do it. If you want to make a picture book, it'll do it. It'll pretty much do anything. It's not the best at anything, but it's the second best at everything. Okay, so here's my little black box that's not black and red stuff. But this is, LabJack U3 high voltage. This is about $160, I think. I'll put something in there in the corner. And it has a bunch of data acquisition stuff on it, which is super nice. And it has expandable cards on there, like amplifiers. A bunch of little dip switches in there. I don't know if you can see them, but change the amplification rate. So I have my linear transducer here. So you could use a potentiometer, you could use temperature, pressure, whatever. You can use this for lots of stuff. I intend to use this for lots of other things like the flow bench and my spring pressure, spring rate measuring machine. Anyway, I could use this for lots of stuff, but I kind of bought it specifically for this particular thing, the Shock Dyno. This is the load cell that I got and the data sheet for it. Pretty boring stuff, but anyway, and this is the user interface that it comes with, which is it works pretty good. So as you can see, I can start streaming, and I'm not any kind of expert in this, but the linear transducer is there. It's an 8-inch one, so I don't have to worry about changing it. But so that's the linear transducer, and this just adds like a strip chart recorder, and it's recording. Once I stop streaming, it'll save the file. And then my load cell here, when I squeeze it, it's the red line. Yeah. Let's make those so they're kind of the same height. So you get because I can only, whatever my Kung Fu grip is, that's how much force I have, which isn't that much. So, and that's the load cell. So if I have the data for both of those, I can plot that out in Excel and make a fancy force versus velocity curve.